Good afternoon, everyone. Welcome to my talk. This talk is on software regression testing powered by parallelization windows. This is the topic of my PhD thesis and also this synopsis meeting. Let us first look at what drove me to choosing this topic for my thesis. Let us first consider a function fx 2 plus x which has changed to 2 star x. So this plus has changed to star. Now whether to call this manipulation of the function as progression of the function or not, we need to test it. So we have two test cases. These are the inputs for the function 2 and 4. And the expected output corresponding to the older version of the code is 4 and 6. Now the observed outputs, when we test the new version of the code, we see that there is a discrepancy at least for the test case, second test case with input 4. So 6 has changed to 8. So this test case has failed. However, functionality wise, we see that the test case with input 2, F2, the output is 4 is still intact. So functionality is intact for this test case at least. But a failure, functional discrepancy is revealed when the expected and the observed output do not match. So how do this relate to software testing? So in this situation, we see that we need to be thorough with our testing. Otherwise, we would miss a failure, and that could be a blunder. Because in safety critical systems, that might cause catastrophic failures. Now, to do this thorough testing, we have to be as thorough as possible. We need to execute all our test cases at our disposal, which can be as expensive as this industrial example where test all took 7 weeks to complete. So there are solutions, sophisticated solutions to this problem. First one is regression test selection, RTS, regression test prioritization, RTP, and regression test suite reduction. So in this thesis, we will be dealing only with selection and prioritization, and will involve parallelization windows to aid them, to accelerate them. So let us now look at the software setting. So we have one source open C source code v0.c, which takes as input a number, and if the number is even, it performs something in the if part of the code. Otherwise, it goes to the old part of the code, else part of the code. Now the change source v0 has been updated to v1 in terms of the update at line number 11. N equal to n minus 32,000. So this is the statement that has been introduced in the if part of the code. Now, if we had 10 test cases in the original test suite at our disposal, do we need to run all of them? Certainly not. We need to run only those test cases that touch only the if part of the code, because that is where the change has occurred. And if the change could lead to an error state, that must be propagated to the output. And this thing is only possible when we activate the fault, if at all the fault is there. So to activate the change, we need to test only this, we need to follow only the if path. So for our simplicity, we have in these 10 test cases, we have randomly generated integers from 0 to 99. So 5 of them are even integers and 5 of them are odd integers. So what you need to do is to select only these test cases which have even integers as input 0, 4, 16, 15, and 2. All other test cases are odd integers. So you see that we can also remove the 50% of these test cases that are not relevant. So these regression test cases are now only 1, 3, 5, 7, and 9. And what are we testing? We are testing for failures. So a failure is the event when the current service, so the current service corresponds to the output of the new version of the code. So this new version is the version under test. That output deviates from the expected output. So expected output corresponds to older version of the code. So if there is any discrepancy, that certain test case under application is said to have failed. Now this statement, testing may consume over 80% end-to-end and 50% maintenance cost. This is the cost involved with software regression testing, and this is the goal which drove me into choosing the acceleration of this process using parallelization windows. We'll see that in after a couple of slides. Let us first see what the three different phases of regression testing, because the end-to-end involves a lot of phases. We need to first go phase by phase and then capture them using parallelization windows. Let us first see what are the different phases. So the offline phase is the first phase. which involves code instrumentation. So by code instrumentation, I mean inserting probes into the older version of the code at certain places and execute all the test cases, so that in that exercise we get to know the test coverage for each test case. The coverage in terms of the code elements. So which test case part tests which part of the code. So we have test case and then we have basic blocks here. So if we have inserted probes in the basic blocks, which will be able to print their labels. So if we execute the test cases, all the test cases, for each test case, we'll get to know the labels of the basic blocks executed by the test case. So we have this coverage map, test case to basic block coverage. Now the online phase starts. The online phase, the name of the online phase is because this is the time when the new version of the code has come in. So the updated version has come in and identify the changes, changed code elements or changed LTTs. We use the reverse mapping, code elements to test cases instead of this test case to code elements, to select only those test cases that are relevant for testing the regression. That is, they are change exercising. After the selection, we need to execute them. So that happens in another phase, that is the execution phase. So these three phases, offline, online, and execution, follows this order, and this is according to conventional regression test selection. So this regression test selection means select and execute only those test cases that are change exercising. So this change exercising has been done in, so that selection has been done in the online phase and execution has been done in the execution phase. So this end to end means the first end is at the top of the offline phase. That is the beginning of the offline phase. And the second end is at the end of the execution phase. So this end to end is the entire time elapsed from the start of the offline phase to the end of the execution phase. And we accelerate this, we reduce this time using parallelization windows. None of the prior works targeted phase-wise parallelization. So we see that there is a certain sequentiality involved. So offline should be followed by online, and then online should be followed by execution. So we cannot run any of this in parallel. But inside this offline, inside these three phases, there are certain subcomponents which can themselves be parallelized. So we'll see in short how to do that. Now we propose parallelization windows to tame the problem, to accelerate the subcomponents that are indeed parallelizable. Some of the subcomponents are inherently sequential. We will discuss that when we delve deep into this diagram. And we assume that all test cases are independent and can be executed in parallel. So by independence of a test set means that if we have two test cases, T1 and T2, T1 writes to a file and T2 reads from that file. So these two cannot be executed in parallel. So there has to be some sequentiality. So to respect the sequentiality, we need to execute them in sequence. So if we have independent test cases, which will not be the issue if we for the shared things, and we execute the test cases in terms of different isolated address spaces and in terms of multiple processes, parallel processes. So this is the parallelization window, how to execute the selected test cases on a sequential execution unit. So 1, 3, 5, 7, and 9, this is the order in which they will go into the execution unit, and this is the order in which we will observe the output. So that is sequential. Now, if we have more execution units, 5 execution units, we can choose a parallelization window of size 5. So the size of the window is the size of the batch size, that is the threading factor. So we allocate that number of threads to that windows. So we have a window of size 5, we have execution units also number 5, and we have 5 threads. So we launch each test case on each execution unit. Now we may not have all the way through that many execution units at our disposal. So what we do is we can decrease the size of the windows. So if we have 3 execution units, we use a chunk size of 3. That is the window size of 3. And what we do is we chunk this sequence of sequential order. That is if we treat this as an order permutation, we chunk that sequence in 3, 3, 3. Note that the last window might have some fragmentation issues, because if it is not multiple of 3, there might be some problem. So you see that in each window, inside each window, parallelism exists. That means 1, 3, and 5, they are executed parallelly. But the first window must finish execution before the next window in sequence starts executing. So there is a combination of prioritization and parallelization. Now the offline, online, and execution phases forms the different phases of the regression testing, and you can see that there is a feedback, and this forms the regression testing cycle. Our first work introduces, using parallelization windows, the acceleration of these different phases, phase-wise, and Hansi and Colosseum are our second works, which contributes mainly to the online and execution phases. This is because Hansi and Colosseum are involved with test case prioritization. So it forms a prioritized order such that if we execute test case in a certain order, and if we stop at some point of time, if we have a certain strict test execution budget, up to that point of time, what we have executed, we make sure that they have indeed tested the most important parts of the code. So there are heuristics to do that, because a priori we do not know which test case will fail. So we need to have heuristics for prioritization, and accordingly, the prioritization can be coupled with parallelization. So those prioritization goes to the online phase, parallelization goes to the execution phase for Hansi and Colosseum. So let's just first delve deep into MATA, the first work, the phase-wise acceleration of regression testing. So the first phase is the offline phase, where we have only the old version of the code. We get the LLVM IR for the old version of the code, v0.c to LLVM. So C to LLVM code is generated by Clang. Now we use the LLVM IR so that multiple different source codes, the C family of languages, all can be normalized to one intermediate representation. So we instrument this LLVM IR, we generate test coverage, and we create a forward map, that is the mapping from test case to basic blocks. Now note that the shaded components are where the parallelization opportunities lie and where we implement parallelization windows, and others are all inherently sequential part. Now note that this arrow means a dependency diagram. So this first component must happen before the second one. So instrumentation must happen before getting the test coverage, and then this. So the offline phase has an arrow outwards going to online phase. So this offline must happen before the online. So the online phase, where the new version has come in, we get the LLVM IR for that. We first check whether there is any discrepancy in the global section of the code. The global section is the IR. So because there are global variables in the IR, so in the C code, what we do is, if we have any global variable affected, because it has a global scope, that is going to potentially affect any code inside that is further going. So we treat that global section as a super block, that is a basic block or a startup block which executes even before the main starts executing. So since all test cases will touch that part of the code, the global section where the global sections reside, we do a fallback mechanism, and we say that if any global is affected, or if at least the global section is affected, we go for retest all. So if we see that there is any comparison in the globals, that if there is affected, we fall back to retest all, and we just go a bypass over here to the execution phase. Otherwise, what we do is we fold the temporaries in both these IRs. Since we have two threads here, because there are only two versions. So folding of temporaries is necessary to avoid the unnecessary diff. So unnecessary diff happens because Clang generates some temporaries, percentage followed by any number. So percentage 15 and percentage 16. So percentage 15 in the older version of the code and percentage 16 in the new version of the code, in the IR, maybe source wise same, but IR wise they're different. Now since we are going to take diff of the IR, we need to have one way out so that we can fold these numbers, temporary names, into some character. So what we do is we fold them into dollar. So percentage followed by any number is folded to dollar, and we finally perform the diff of the IRs. From the diff we get what are the affected basic blocks that got changed, added, or deleted. So because we want to do parallel processing, we need to have arrays, and we create an array of affected block from the set so that independent locations can be accessed in parallel, and we prioritize the test cases. Prioritize this and give score to individual parts of the array. That means we access independent location of the arrays and each independent location. So that array we see like an adjacency list now. So each location of the array is a header to a linked list. So a linked list is the sequence of basic blocks. So we award values to this each of these uh, location of the array. That means that test cases, we award these test cases, and depending on the score of these awards, we determine the priority. And we prioritize the test case, and we sort the test cases, and we execute these test cases in this order in the execution phase, where we execute test cases and check their outcomes. If there is a discrepancy, the test cases said to have failed. So this is the total diagram of offline, online, and execution phase zoomed in. Note that the shaded portions are where the parallelization opportunities lie and where we have implemented, where we have included the parallelization windows. Others are sequential part of the component, inherently sequential part. Now comes the contribution HANSI. So this is the consensus test case prioritization. The next two contributions mainly focus on this prioritize, test, and execute and verify. So the online phases. So because we have the prioritization here, prioritization for the next two. So this prioritization and execution, parallel execution are the focus of the next two works. So let us now look into detail for what prioritization is using HANSI. Now prioritization is based on some heuristic by which you execute those test cases earlier which are capable of revealing failures. So that we have, let's say we have 100 test cases and we have selected 10 test cases, but each takes 1 hour to execute, but we have a budget of 3 hours. So within that 3 hours, we need to make sure that whatever we execute, whatever test case you execute, they have tested the most fault-prone part of the code. So you need to have some heuristics to determine that means we award a test case, determine the quality of a test case, and we execute those test cases, high quality test cases, earlier in the timeline. The timeline means earlier in the execution phase. So whatever the literature we have in software regression test prioritization, we have multiple different heuristics because a single heuristics may not perform optimally in on scenarios. So different heuristics may lead to different effectiveness of the heuristics. So the effectiveness of that prioritization. So our intuition is that a consensus of those different orderings may be better. So let's see with this example. Going back to our example, we have 1, 3, 5, 7, 9 as the regression test suite. And there is a prioritization heuristic 1 which says you execute test cases in this order: 3, 1, 5, 7, 5, 9, and 7. And red ones are the failed test cases. So we see that test cases are failing at alternative positions for heuristic 1 if we follow this heuristic and execute test case according to its opinion. Now another heuristic comes in and says you execute test case in this order. Another heuristic also comes in. So these different P1, P2, P3 are different permutations of 1, 3, 5, 7, and 9. Now, if we combine them, if we combine these different permutations, these different orderings, and come up with a consensus of the ordering, here it is Kemeny-Young consensus. We see that if we execute only the first two test cases, now suppose if these test cases each take 1 hour to complete, so according to consensus, if we just according to the consensus prioritization, if we execute only the first two test cases, we get 2 failures revealed. Whereas in the others, we have only 1 failure revealed. So we see that this consensus prioritization is closest to the optimal prioritization. So in optimal prioritization, what we have is that the test cases are failing consecutively from the beginning. Now, this is something which is fictitious, and we do this as a baseline just to compare, just to make sure that how my prioritization is close to the optimal scenario. Because a priori we do not know which test case is going to fail. So we see that a dense distribution of test cases failing near the beginning of the timeline is a desirable effect, and consensus may be better. In this case, it is better. So major contributions of Hansi is that we perform a study on hybrid prioritization. That means hybridization of two different heuristics. Use one weighted factors, so that weight sum of the weights is the hybridization operator. Weighted sum hybridization of relevance and confineness. Relevance and confineness are different heuristics that we have uh, proposed in our earlier work. That is the first work, Mahatab. And then this is the first component of ANSI, hybridization of that using the alpha weightedness. That is, alpha is the weight given to relevance, and 1 minus alpha is the weight given to confinedness, so that this to sum up to 1. So confinedness and relevance, hybridization of this using alpha hybridized relevance confinedness. And then we have consensus, priority consensus of this individual, which you will see when you discuss the experimental results. Consensus regression test is prioritization. We also introduce Hansi distance between two prioritizations to measure the quality of the final consensus. The consensus that you obtain from individual orderings, the distance of that consensus, that is the distance in terms of Hansi distance. So Kendall distance is one distance which which accounts for the number of inversions. However, how these pairs are separated into different orderings are not taken into consideration. So to address that issue, we propose Hansi distance. We also include a metric EPL omega, which is a cost cognizant metric, and it measures the effectiveness of parallelization, and which is in combined with prioritization. So parallelization prioritization effectiveness is given by EPL, and the value is normalized, and it is between 0 to 1. The closer the value is to 1, the better is the effectiveness, better is the prioritization parallelization. Now to move on to the next contribution, we have delta displacement based prioritization. Now, if we go to the offline phase, we show that we generate the test case coverage. So test case coverage here is in terms of basic block coverage per test case. So for this test case TI, we have B0, B1, B2, B3. So this is a linked list. This is a linear sequence of basic blocks. And this is without repetition. Note that a basic block due to um, a backage in the control flow graph because of the loops may be executed multiple times. However, to simplify these things, what we do is we capture only the first occurrence of that basic block in the whole execution sequence, so that there is no loop. So this linked list is just a single linked list is just a linear order where which is loop free and in order. So these orders are the first occurrences of all these individual basic blocks. Now let us first see what this partition is about. But before going to that, we need to motivate ourselves. Why do we at all go for this partition? The notion of change, propagation to the output, is closely related to the failure observability. Because if the change that has occurred in the test execution path, that change is in error state, if that is propagated to the output without getting lost, we will definitely observe a change at the output. So the output here is associated with the terminating basic block. So B0 is the initiating basic block and BR minus 1 is the terminating basic blocks. Or all internal blocks are intermediate basic blocks. So the deltas, shaded basic blocks here, are the blocks that got affected. So what we want is that we need to go to the first affected block from the starting. We need to go to the first affected block. So this is the change, that is the fault activation site. So we need to go to the fault activation site as quickly as possible. So this displacement A, that is the hops, the displacement distance from the first block, should be as minimum as possible. Now fault activation is one thing. Now the fault must propagate as quickly as possible to the output. So to do that, since we have intermediate affected basic blocks, the scattering between them, scattering among them, the average of this should be as minimum as possible. So that wise, we have the section that is the value of B, that is the second partition. The third partition, whatever we have aggregated, whatever states that we have aggregated up to A and using A and B up to this point, that must be propagated as quickly as possible to the output. So the combined effect of A, B, C, there is the delta displacement triple. If we multiply them, we see that value overall which is less. If we have that value less, overall shorter displacement has a low chance of transferring, a low chance of effectiveness by computational masking, and a high chance of transferring that affected state to the output as quickly as possible. This is because the shorter the length of the path, the lower is the chance of computational masking. So by masking, I mean to say that the error state is propagated to the output without getting lost by other intermediate computations, which may turn it over. And this is really bad, because if that error state is lost, the test case might actually pass, which should have failed. So that is coincidental correctness. So this is the immunity. So this displacement triple and this formulation helps us approximate the immunity of a test case to this computational masking. So Colosseum, the third work, where we have the first prioritization strategy, which takes into account the position of the change code elements along the execution path of regression test cases. So the position of these deltas A, B, and C along the execution path of the regression test cases, because these are the deltas are the only way which we can observe where the changes occurred. And as I said, this value d-val approximates the immunity to change masking, and that is also helped by displacement parameters alpha, A, B, and C. Parallelization wise, we generate a sequence of test cases execution sequence, which we say prioritized window execution request, which is a static request, and because that is platform independent request, which can be realized in many different ways by many different hardwares, because all hardwares are not equally capable, and we need to be sure that if we have a parallelization window of size 80 and we have maximum of 40 threads at our disposal, 40 core machine, so we cannot just directly launch for 80 threads. That will lead to context switching overheads, and that will actually be bad. So this prioritization windows, there is a one-to-many mapping to different realizations, and this helps us tame the execution phase much more efficiently. So we move on to the experimental results now. So we have two different benchmarks, two different sets of benchmarks. One is from the SAR repository, which is used in classical days of software testing. And then we have this modern GitHub projects. Total, we have 20 open source projects. For Mahata, we observe end-to-end speedup of 4.72 with 16 threads for the SAR projects. And for GitHub, we have 3.04 x speedup with 32 threads. For HANSI, we have 13 individual prioritizations. So like, for example, we have the 5 different test cases, 1, 3, 5, 7, and 9. So that these are the test cases that need to be executed. But in which order, we employ 13 different individual prioritizations. So they'll give independent, so these are all independent heuristics. So they give their opinion on how to execute. So they actually, so all of these return 13 permutations of these 5 test cases. And we have employed 6 consensus operators. Each consensus operator rank aggregates all of these 13 permutations and finds a consensus permutation. So these consensus operators and their effectiveness wise ranking here is consensus by harmonic mean of ranks, geometric mean, consensus by arithmetic mean of ranks, border count consensus. So this is actually from 1778, consensus by median of ranks, and consensus by Kemenian consensus. So this Kemenian consensus is from 1959, and this is the consensus that I showed in our example in earlier slide. And then Colosseum, delta displacement based prioritization, where we have 4 state-of-the-art prioritizations, and Colosseum was able to beat all of them in terms of 11 out of 13 prioritization metrics. So that is 84.61% success rate in terms of the metrics. So there were 13 metrics employed, 13 effectiveness metrics. According to the 11 metrics, Hansi was Colosseum was able to outperform all the four state-of-the-art prioritizations. And for according to two other prioritization metrics, it Hansi performed the second best. Not Hansi, sorry, it will be Colosseum performed the second best effectiveness. So to conclude, we discussed the problem of software regression testing. We discussed the concept of parallelization windows. We discussed how our contributions, Mahatab, Hansi, and Colosseum, are weaved together in this thesis. Thank you.